So starting from where we left off in last video, we're going to be taking the data that we imported and we're going to model it using this Antoine equation right here. I added a couple imports from the JAX menus from NumPy as well because we needed the minimize function to do our model for the Antoine equation. Also, we need to make sure that our data is in horizontal vectors, which we already have, or horizontal arrays, which we did here. However, our pressure data needs to be in log 10 because that is what our Antoine equation uses. I'm just going to change the name to the log of pressure values. And to do this, we use NumPy function of log 10. And the reason I'm multiplying by 1,000 is because the data we imported from the Dortmund data bank is in kilopascals, and we only need it in pascals. So this will get us our pressure values. And for this, we're going to graph it. We're going to graph our current values that we have right here. Make a subplot because we will add to it later. Underscore. With one row and one column. And we're going to make it a scatter plot. With our x-axis equal to our temperature values and our y-axis equal to our log of pressure. And then because we only want the data points and not a fit line, we're going to change the mode to markers. This will get us, should get us, model of our data mode equals markers. I always forget that. And there we go. So we have a graph. I'm not going to change the color because I like how the white graph pops against the dark background that I'm using for collaboratory. So if you notice, we have our data points that were imported. However, a realistic application of this, we would have to guess maybe a value in this area between our 343 and 412 on the pressure. So the Antoine equation gives us the relationship between temperature and pressure of an ideal, or not an ideal, but a pure substance, which is what we're dealing with here in water. And by creating a function for the Antoine equation, we can help model that accurately. So let me create a function here for the Antoine equation using the variables a, b, c, and then our temperature values. Those are periods instead of commas there. Okay. And then we're going to turn our Antoine equation. So a minus b over t plus c. I've done this a few times, so I know that's right, but just to check, it does match what we have right here. Okay, so run that. And the way we figure out A, B, and C, which at the moment we have no way to figure it out right now, is by doing something called sum square error, which finds us the error between three different guessed values, which I'm going to create right now as variables. And so it finds the error between our guessed values and then the ideal. And by minimizing that, then we can find and fit a line to where our estimated values are. But these need to be put into a horizontal vector so that we can input them correctly and easily. Make sure that's all good. All right. So now we're going to do a function for our sum squared error values. Okay. So we're going to model that the pressure data using our guesses that we guessed above, and this will correspond to the guesses we made and put in the vector. So you can change these guesses and then run it again, and you can find the error and try to narrow it down. But this will give us our exact values once we're done with this, so there won't really be a need to. However, if you are just trying to find the values, you can continually guess and see if you can minimize the error, and that way you can get your values just through guess and check. So these correspond, this P model corresponds to the A, B, C, and T up here. So this is going to be our guess A, guess B, guess C, and then we're still going to use our temperature values from above. Make sure that's correct. Okay, and then whenever our error be the sum of what we just calculated minus our original log pressure values, and we're going to square that. Return our error. Shift enter. Okay, and then our values to display them. Now we're going to use the minimize function. Minimize. Alright. So you take our square error function from above, our array, and then our arguments are going to be the original plot we had above. Equals. It's going to be T comma log pressure. It's going to be capitalized. And then our tolerance is just going to be a really small number. So it's going to be 1 to the negative 10. And then we need the jack function. Equals jacks. And this is going to give us a gradient, which is basically going to do the derivatives, which is going to help us narrow down the error. And basically, this is just going to make it able to plot the line for the Antoine equation. Okay, and then if I display the value that we get, the values that we get, shift enter, and yeah, so these are going to be our values from the guess. These are going to be our actual values here. And now using this, we are going to be able to create a smooth plot of the Antoine equation. And to do that, a model of temperature values. Do one space. Right there. And basically what this part is saying is between the values that we have, if you take a given value and then the value right before it, those needs to be brackets. Jeez. Okay. Take that value, a value, and the value right before it. We're going to want, say, 1,000 values in between those. And that's just going to make it a much more smooth line, so we can get as many data points as possible, just for precision. And then we're going to add to our scatter plot. Scatter. So our new x is going to be the t model that we just created. And then y is going to be model of the values right here. X and then comma t model. Make sure I type that out right. And this time our mode is we're just going to make it a line. There needs to be comma. Because we want to actually graph what the pressure is going to be for every given temperature of our pure water. So the mode is going to be lines. And then if we want to, we can create a name for this line. And yep, so this is now gives us the full line, which connects with our values. But then also gives, if you hold your cursor over, can't even get that sound, that for every given temperature, you can find the pressure. And this goes all the way up to our last data point.